Silly quail. So I'm going to show you that you've been taught exponents, how exponents work. You've been taught the wrong way. Numerically, of course, what you've been taught works just fine if you've taken, high school math or whatever. But if you live in an English-speaking country, I can pretty much guarantee you that what you've been told about exponents is actually not how they work. So what I've seen, and if I'm wrong about this, that's fantastic. I'm totally fine with that. That's a good thing. From what I've seen from English, like textbooks and whatnot about exponents, is that when you raise a number to a power, you take that number and you multiply it by itself power number of times, right? So something like 3 to the 4th is 3 times itself 4 times. Now this is a problem because if we take 3 and multiply it by itself once, that is not 3 to the 1st, that is 3 squared. And if we take 3 and multiply it by itself twice, that's not 3 squared, that's 3 cubed, because you took 3 and then you multiplied it by 3 and then you multiplied that by 3. That's taking 3, multiplying it by itself twice. So the words that we say are different from what we're doing. In some other languages, I've seen it described much more accurately as like 3 times itself 2 times for 3 squared. Or, I mean, what is it? 2 3s multiplied together, something like that. Something like that. Like, you can get it to make sense. You can get it to be correct. But there's still a piece missing. Even with all of this, there's still a piece missing. So, say we'll use, say, 3 to the 4th as our sample there. So, I don't know if the camera can really see that. 3 to the 4th power. Okay. So that's going to be, numerically, what you have been taught about this, just fine. Numerically, just fine. Logically, philosophically, not so much. Okay, so this is, come on paper, cooperate with me. 3 to the 4th, there's 4 3s multiplied together. That's a fine way to say that. If you've heard it described that way, good, that's fine. There's no problem with that. Well, there is a problem with that, but as far as a numerical analysis and being told that this is how it works, that's fine. So we have 4 3s, and there's multiplications between them. Okay, so the 3 means something, it's the thing that we have a bunch of. The 4 means something, it means how many of the 3s we have. And in the spaces between, we drop in multiplications. But because of the way this works, we're getting 3 multiplications, not 4. So it is not 3 times itself 4 times. There's only 3 multiplications occurring under this, what's happening here. I've left a blank space here. You probably noticed this. There's a weird blank space right here. That is because there's actually an entire component of this whole thing that is missing. We'll get to that in just a moment. And now, so another thing that you've probably been told about exponents is that anything to the 0 power is equal to 1. And you've never been given an explanation for why. You might have enough experience with math to have kind of looked at it and convinced yourself that it must be true. When you look at how functions behave and all sorts of things, it definitely looks like it should be 1, at least almost always. But why are we saying that something to the 0 power is 1? Well, ultimately, for the most part, it's just because somebody said so. That's not a very good reason to do anything, especially in a field where we allege we have this cultural expectation that the things that we're doing here, we're doing for reasons. It's not just, oh, anything to the 0 is 1. That doesn't, why? Why is that, that doesn't make sense. That's not a good reason, right? It can be fine that that's true, but we want to have some sort of a reason for it sort of fleshed out. Okay. Now, another thing that you've been told, I'm sure, is that something to a negative exponent is the same as 1 over the positive exponent. So again, I've left a giant space here, but 3 to the negative 4 equals 1 over 3 to the positive 4. Okay? Numerically, I have absolutely no problem with this. Let's see if I can make this a little more visible on the camera here. So we've got 3 to the positive 4 is all of that noise. 3 to the 0 is 1. 3 to the negative 4 is 1 over 3 to the 4. Okay? So this is generally, in my experience anyway, what textbooks will tell you about. They'll go into a little more detail about a few other things, but the gist of everything that they're telling you is this. And you notice I've left some blank spaces here because there is more to this story, and when you see it all, this is all going to make a lot more sense, including why this is a 1. Why something to the 0 power is a 1. And this actually turns out to have some ramifications in higher level mathematics that, to my knowledge, is actually controversial among professional mathematicians, even now, today. So, yeah, this is interesting, and I kind of think that the reason you haven't seen what I'm about to show you is because it's possible nobody knows about it. I discovered it myself, and I've shown it to some people, and for the most part, they recognize that I kind of have a point here, but they've never seen it themselves either, and it never occurred to them to think of it this way. Okay, so first thing we're going to do, here I have a 1. When I have a 0 exponent, I have a 1. When I have a negative exponent, I also get a 1. So why don't I have a 1 up here? And what would happen if I did put a 1 in here? Okay, so let's try this. If I put a 1 in here, then I get a 1 everywhere. That's, unto itself, it's not necessarily really going to be all that groundbreaking or useful, but let's try it. Let's see where this goes. If I put a 1 in here and I'm multiplying by it, that does not change this numerically. Anything times 1 is itself. So if I go ahead and multiply by 1, that's not going to break this at all. It's going to be exactly the same thing numerically. But notice that something has now happened. I have a 1 here that appears to be my starting point. I have a 1 here, and nothing else happened. I have a 1 here. Well, what if we kind of drop this in sort of the same way? And now look at the semantics of this negative. What does negative actually mean? Well, across mathematics, and basically logic, all of logic, but definitely across all of mathematics, what the negative actually means is to, like, the opposite, like flip the direction that you're going in, right? So a positive number, when we take the negative of it, it flips direction, right? So a positive goes that way, a negative flips direction, the negative of a negative, right? So you take a positive, you flip it negative, and then you flip that with another negative. So negative of a negative is positive because you only have 2 choices of direction. If I flip direction twice, I come back to where I started. So negative, negative, or an even number of negatives just yields a positive because that's all that the negative is doing. The negative doesn't actually, unto itself, have a direction. What it does is it takes the direction that you're already given and it just flips it. Here, the thing that we're doing, if we look at this now, what it looks like this means is we start with 1, and we multiply it by the base, here 3, exponent times 4. So I take 1, multiply it by 3 4 times. 1 times 3 once, times 3 twice, times 3 3 times, times 3 4 times. There it is. With 0, I take 1, multiply it by 3 no times. So I start with 1, and then I don't do anything. That's why anything to the 0 power is 1. Okay, so now a negative exponent, what were we doing up here? We were multiplying. So the negative means we're going to do the opposite of multiplying. So the way I'm going to write this is technically not correct. Just understand that there should be parentheses. But I'm going to write it in a way that makes it look pretty on the paper, so that it looks like it mirrors this. But understand, I do know that you should use parentheses in order to get it to mean what I want it to mean, but I'm going to write it out. So if we continue this semantic analysis, what this should be is 1 divided by 3 4 times. So if we take 1 divided by 3, then we divide that result by 3, then we divide that result by 3, then we divide that result by 3. That is exactly the same as this. So now I have one way of saying what an exponent is, what an exponent means, that works for all of the exponents. Right? So this also kind of tells us how counting actually works. So you start at 0. You start at 0. You always start at 0. Whenever you're counting, you start at 0. Right, so that first element, that's 0. And then the next thing you do, that's 1, 2, 3, 4. So 1, our 0th element, times 3 once, times 3 twice, times 3 3 times, times 3 4 times. We're done, because we did 3 to the 4th. 1 times 3 4 times. Here, 1 times 3 no times. So we start with our 0th element, 1, and we stop. So that's all we do. We come up to the starting line, and we just fall over dead or something. Like that's it. That's it. We're not running this race. We're good. We just get to the starting line. That's good enough for us. Over here, 3 to the negative 4th. I come up to the starting line, 1, and now I'm going to divide by 3. Then I'm going to divide by 3 again. Then I'm going to divide that by 3. And I'm going to divide that by 3. So I get our starting point is 1. It's our 0th term. And I want to multiply it by 3 negative 4 times. Or divide by 3 4 times. 1 divided by 3 once. Divided by 3 twice. Divided by 3 3 times. Divided by 3 4 times. And if I put in the parentheses to make this look correct, it wouldn't be as elegant looking. It wouldn't be as pretty. So I understand that, 1/3 divided by 3. This isn't how you would write that. Probably this isn't a good way to do that. It's not unambiguous. I understand. But now you can see that every single piece here has a direct correlate in all of the other ones. So trying to say something like, well, 3 to the 4th means 3 times itself 4 times. Okay, clearly that's wrong. We've talked about that, because that would, if you take 3, multiply by itself 4 times, that would actually give you 3 to the 5th. So it's the wrong thing to say. Also, where is the 1 coming from? Why is something to the 0 power equal to 1? The way that that's being said, there's no explanation for the 1. If instead we say what an exponent means is we take a 1, we multiply it by the base exponent times, Now it works for all possible cases. And that defines anything to the 0 power as 1. So there's no like trying to find the limit of what it is, or what something to the 0 is, trying to find the limit of that. That's not the way to approach this, because we now have a defined way based on reasoning. You can look at this, and this is a correct definition of this, because we have all of this this going on here, all of this parity going on. Now, we can actually show that this is physically real if we look at geometry just a little bit. So, first off, this is going to seem kind of weird. Like, why am I showing these? But let's take a look at, first off, we're going to look at 0 dimensions. We're going to grow from 0 to 3 dimensions. Maybe we won't go all the way to 3. I don't know. I haven't decided yet. But we'll at least go up to 2 dimensions so you can see what I'm talking about, why the 1 is physically real, and you can demonstrate that. Okay, so in 0 dimensions, the only thing that can happen is you either have a point or you don't. So the question is about existence. And that is in 0 dimensions. Okay, so our object will be a point. So that would be like, like a little dot, right? And then what we can say about that is, does it exist? If so, we'll call that 1. Does it not exist? If there's nothing there, if the point is empty, then we will say that its existence is 0. It does not exist. So 1 means something. The lighting is terrible, I understand. Also, the camera can't focus for shit. And 0 is nothing. So nothing, I don't think anything here should be groundbreaking, but all right, we're talking about existence in 0 dimensions. So we have a point, bam. Here it exists, there's something there. Here it's empty space, so there's nothing there. Something is represented with 1, nothing is represented with 0. Kind of right off the bat, you can see why multiplication grows from a 1 and why addition grows from a 0. So when we're talking about exponents, which is relating to multiplication, it's iterated multiplication, you should start with a 1. You should start with something. It kind of makes sense. But now we can take that point, right? So say we've got a point right in there, and we take that point and we stretch it, and we get a line, right? So now we can have length on our line. And that's going to have 1 dimension. Which we will call, in this case, x. So we've got length, that's 1 dimension, and we're going to name that dimension x. So our object with length, not surprisingly, is going to be a line length. Oh. Okay. And its length is x. God, this camera can't focus for shit. Alright, so we have a line, this guy here. We took that point and we just stretched it in a direction. And we stretched it the distance x. So what we can do, talking about length, we can say, okay, our length is, well, it's for that entire length x. For that entire length x, there are points that exist over the entire length. There are no holes. So we get all of it. So we get 1 times x. Or that is x to the first power. Because we're in 1 dimension with x. X to the first power, we have just shown that it is 1 times x. So far, it's probably not super convincing that that 1 means something. And similarly up here, this is going to be, this 1 is x to the 0 power, because it's a 0-dimensional version of x. It's a 0-dimensional version of this line. So this 1 is x to the 0. X to the 0 is this 1, this something that you're starting with. Okay, it's going to become a lot more convincing when we get to 2 dimensions. Right now I'm just kind of like, oh yeah, this is how it works. And you shouldn't believe me at this point. I've not said anything that should really convince you as far as the geometric analysis here. Okay, so if we take this line and we pull it in a perpendicular direction, we get a sheet, like a rectangle, like this guy, like this piece of paper. And its natural unit is going to be area. And that operates in 2 dimensions, which we will conventionally call x and y. Okay, so we've got 0 dimensions. There are no dimensions, so we don't name it anything. We don't name it, there's no dimensions to name. For length, we get 1 dimension. We call that one x, conventionally. For area, we get 2 dimensions, and we call that xy, conventionally. Alright, so kind of your simplest object in 2-dimensional space is going to be a rectangle. So we've got x in one direction, and we've got y in a perpendicular direction. X horizontally here, y vertically. So we can talk about the area of this as all of x times y. Or area equals 1 times x times y. And I think the more clever of you will understand why I'm saying all of, because once we start looking at other 2-dimensional shapes, we're not going to take all of it. Okay, there's going to be a special version of the rectangle, which is square. And that's, both of your sides are the same length. You have, we'll call it x in this case. We have x in both directions, horizontally and vertically. So your area for this guy is going to be all of x times x, or x squared. And the name of that exponent, that 2, is the name of the shape that it's describing. So we have a square, x in that direction, x in that direction, or whatever's 5, 20, it doesn't matter, whatever number you want. The area of that square is going to be all of the value x times itself, or x squared. Okay, so we don't have to take all of it. We could cut it. We could throw away part of it, right? The simplest one, I think, to see is a triangle. So we've got, I've built here a right triangle, but the same sort of thing applies for any triangle. Okay, so we've got a triangle, and I have it situated inside, so the dotted line is sort of the missing part of this rectangle that it lives in. So we have x this way, and we have y this way, just like we do on our rectangle. And we basically fold it corner to corner, just cut it off, right? So what we've done is we've thrown away half of it. So the area of this guy is 1/2 of x times y. 1/2 of it instead of all of it. All of it is represented with the 1. Half of it is represented with a half. Bizarrely enough. Now this means that for any sort of shape, we actually get a shape constant. And that shape constant should be between 0 and 1. For the rectangles, it is 1. For any other shape, it's going to be some fraction of 1. Something less than 1. So now if you think about this for a moment, this means that the shape constant for a circle, or in other words, the fundamental circle constant, has to be smaller than 1. I'll give you a second, because I'll guarantee you, your entire mathematical career, you have been told that the fundamental circle constant is 3.1415, etc., which is larger than 1. So either I'm completely full of shit, or there is something more elegant here going on than what you have been taught. Alright, so we'll actually look at that specifically right now. Okay, so we're looking at just random rectangles. The random rectangle version of a circle is an ellipse. So we'll look at that. Ellipse. So we got the bounding box, the box that it lives within. And draw the ellipse inside of it. And we still have the horizontal direction. Here, the way that I've drawn it, that's going to be your major axis, is x. And your minor axis, the way I'm drawing it, is y. So you have an ellipse. Assume that I can draw worth a damn. So vertically we have y, just like we do in all of these. Horizontally we have x, just like we do in all of these. Now, if we take a look at this, kind of at a glance, it's like, yeah, you threw away maybe a third of it, maybe a quarter of it, somewhere in that ballpark, maybe a fifth of it, somewhere around there. Okay. But we know that it's basically a modification of a rectangle, so it's going to be the area equals something times x times y. So really the only question here is, what is our shape constant? What is the ellipse constant or the circle constant? It turns out to be the same exact number. Okay, so we want a number that is between 0 and 1. And it's not going to be pi, because pi is much larger than 1, relatively. It's 3 and a seventh, roughly, bigger than 1. It's far too big. But looking at this, it's a decent estimate to say we threw away about a quarter of it. So now thinking, okay, pi is right about 3. There are, we'll get to that. Naively, let's just go with that. When you look at a rectangle, there's 4 sides. There's a thing we have 4 of. So, okay, maybe this 3 something and that 4 something, maybe those are related. Turns out they are. So let's just try. Let's just try pi divided by 4. What happens if we do that? Well, it turns out that that is exactly correct. That is exactly the fundamental circle constant. Pi on 4. And the special case of the ellipse, just like the square was the special case of the rectangle, the special case of the ellipse is going to be the circle. So that guy lives inside of a square. So we've got x horizontally, we've got x vertically. And the area of your circle is going to be pi on 4 times x times x, or pi on 4 of the square that it lives within. So just over 3/4 of the square that it lives within, which is really, really handy. Say your side length of your square is 4. The area of your circle is pi. Well, no. Hang on, I'm stupid. Say the side length of your circle is 4. Okay. Back this up so I'm not so stupid. So you have pi on 4 times 4 times 4. Okay. One of these 4s cancels off this 4. Because anything divided by itself is 1. That goes for literally anything, not just numbers. LeBron James divided by LeBron James is still 1. Alright, so 4 divided by 4 is 1, and when we multiply by 1, as we've seen, it doesn't really mean anything. We can ignore it. Okay, so basically you just have 4 pi. The area of a circle where your diameter is 4 is just 4 pi. If your diameter were 2, 2 times 2 is 4. That'll cancel off that 4 nicely. Now your diameter, or your area, is pi exactly. Cool. Since pi is a button on your calculator, since pi is a number that they pound into your head, that's interesting. It's actually only culturally interesting because the real fundamental circle constant is this guy. Not pi, but it's okay. That's okay. They're all related. This guy, pi, and tau, 2 pi. Tau equals 2 pi. And there's people who are like, oh yeah, tau is the fundamental circle constant. Oh yeah, pi is the fundamental circle constant. You get this argument? Well, this is actually the fundamental circle constant, but they're all related to each other in a very close way. They're all sort of just flavors of this. So whatever, it doesn't really matter. Basically, all of the nice properties are there for all of them, sort of. So whatever, it's fine. Okay, so up here we're gonna say, okay, pi is roughly 3.14. Normally, that's good enough for whatever calculations you're gonna do. For reference, pi on 4 to the same level of precision is 0.785. And if we look at that, 0.785, that is just smaller than 4/5, which would be 0.8, and is just larger than 3/4, which would be 0.75. So, 3/4 is just a little bit smaller, and 4/5 is just a little bit bigger. And these are both, depending on what you need to do, not horrible approximations, right? These are just small numbers that you've understood since you were a very small child. 3/4, 4/5, like the numerator and denominator, as far as those go, those numbers are numbers that you're familiar with. This should be a lot less scary to you than somebody saying, oh, this transcendental number with infinite digits that you can never write out, or whatever bullshit they tell you, like that. 3/4 should be a lot less scary. 75 cents. 80 cents. Okay. That I can understand. That I can deal with. It's somewhere in between those two. That's fine. We can deal with that. And if you need higher precision, your calculator knows pi to a lot more decimal places than this. It's probably going to have something like 3.14159265359 or something like that. It's going to go out, quite a few more decimal places. And it's a calculator, so it's going to be able to handle all of that nonsense. You don't necessarily need to be dealing with it. Just kind of know that it's whatever, that extra level of precision is there if you ever need it. But if you want to do it in your head, these guys are fantastic. Right? Okay. So, what we've seen here is that the square is 1 times x times x. Your line is 1 times x, that's x to the first. This was x squared. X to the 0 is just 1. So this is acting exactly like our exponents, where anything to the 0 is just 1. We just get the fact that there's something existing. There's something there. If I have a higher number of dimensions, then I get the 1 times x, or the 1 times, whatever your base is. And the exponent is just the number of dimensions that you have. There's something else I was going to say. What was I going to say? Oh, yeah. And this we've demonstrated is physically real because we can take that 1 and it actually, as a component, it means something. So if we look at this, as we go down this page, it's all growing from what's up here. This 1 that's up here, it gets inherited by everything else. This x that's here gets inherited by everything else. This y that's here gets inherited by everything else. And when we go into 3 dimensions, the same thing will happen. The rectangular prism, which is in 3 dimensions, is going to be 1 times x times y times z. So the xy gets inherited. It just gets copied down. There's really only one equation for the area of absolutely everything. The only thing that you need to know is the shape constant. And the shape constant has to be between 0, nothing, and 1, or something, or all of it. It's got to live somewhere between these guys. For the rectangles, the cubes, like all of that stuff, the tesseracts, right, hypercubes, your shape constant is 1. For every other shape, it's something between 0 and 1. So now we have one equation that handles all area, length, volume, right? So quickly we'll knock out some volumes here. I won't narrate it as much. So volume is in 3 dimensions. That's conventionally x, y, z. So you have your rectangular prism. So it's got, in one direction it's x, in another direction it's y, and in your third direction that's z. Your volume is going to be all of x, y, z. And when I say all of, I mean 1 times. So we've got this little line box guy, and the volume of that is all of x times y times z. So what has happened is we've taken the rectangle and we've stretched it into a third direction, z, right? So we've taken the rectangle and stretched it into z, right? So all we do is multiply by z. And the rectangle itself was just the line stretched into y, and the line itself was just the point stretched into x. So the fact that we get that 1 goes all the way back to this zero-dimensional existence of a point that was the source of it, that we grew, and we pulled everything in perpendicular directions to get here. And these are the 3 perpendicular directions that we've chosen. The special version of this is a cube, and so that's going to have the same length in all 3 directions. So x, x, x. So your volume here is 1 times x times x times x, or x cubed. So that 3 exponent, just like the 2 exponent, it was called the square. The 3 exponent is called the cube. The first exponent we should maybe call the line. I don't know, but it doesn't really have a name other than first power, something like that. But really, these are the only 2 that have a nice little name like this. If you have a 2 exponent, that's a square. If you have a 3 exponent, that's a cube. And we can see 1 times x times x times x is x cubed. So over here, when I told you with the exponents there was a missing component and it's a 1, that's physically realizable. That's this guy right here. That's that 1, which means take all of it. And in 3 dimensions, we can look at some really easy examples where you can see that this pans out even better. So here we have a rectangular prism, the special case of which is a cube. Kind of like here we had a rectangle, the special case of which was a square. Okay, so we could, instead of pulling the rectangle into 3 directions, we could pull the triangle into a third direction. So the equation for that should just be the volume is 1/2 of x times y times z. Our missing direction is z. So we get our triangular prism. So we've got x, y, z. It doesn't really matter which is kind of the beauty. I like using the variables more than length, width, height, depth. Those words are terrible to use for this because they have meanings in English independent of their mathematical whatever, right? So like the depth of a cabinet is when you're standing looking at it, it's how far back you can reach into it. That's the depth of a cabinet. But the depth of a pool is how far down you can fall into it. Those two directions are perpendicular to each other. And depending on what the object is, the word depth has a specific meaning. It's weird to say, like if a tree falls over, right? If the pencil falls over, I say, how long is it? It's fine. If the pencil's standing up, I say, how tall is it? That's fine. But if a tree falls over and I say, how long is the tree? It sounds weird. It sounds weird because trees aren't long. Trees are tall. Because long is horizontal, like flat like the ground. It's in that kind of a direction. And tall is perpendicular to the ground. Trees normally grow this way. When you kind of your default assumption about a tree is that it's in this sort of orientation. So it has height, it has tallness. It doesn't have length. That's a weird way to talk about it. But a lot of times in math books, you'll see them use words like tall, height, length, long, width, depth. All of those words in weird contexts. And I personally think that this is one of the things that makes math sort of inaccessible to people because for the math problem, they've used the English word incorrectly. And it's a total mindfuck for absolutely no good reason other than the person making the question in that moment was stupid. Like, we all have those moments. We all make stupid mistakes. We all do stupid things. We are all stupid at various times. But this is one that's sort of culturally ingrained in manufacturing textbooks for math, and I think that's a problem, personally. I think that's a very big problem. All right, so volume for your triangular prism. We're just going to copy the triangle. So your triangle constant is 1/2, and we have our three directions, x, y, z. So 1/2, x, y, z. We threw half of it away. We kept 1/2 of it. 1/2 of it exists. Okay. We can also do, say, a cylinder. So let's take that circle and let's stretch it. I'm actually going to, instead of using this, I'm going to go ahead and use this so that it really works for all sort of elliptical tube sort of things. But we'll call it a cylinder anyways, because it works for that too. Just know that in a proper cylinder, two of your directions are the same size. So we've got x, y, z, and your volume is pi on 4 because there's a circle involved, x, y, z. Oh my goodness. We have one equation for everything, and the only thing you need to know is your shape constants. That's it. That's it. That's absolutely it. Alright, it's actually going to get slightly cooler here because we're going to find out what that 2 is. Why is that a 2? Turns out we can know this. If you're familiar with calculus, you might know already. Okay, so kind of our next shape is going to be sort of the three-dimensional version of the triangle. One way you could think of the triangle is that we took that starting line. When we made this rectangle, we started with a line and we stretched it into a second direction. One way you could think of the triangle is that when you pulled it, you didn't just pull it, you also squished it to a point, right? So like this. Here, for a pyramid, the three-dimensional version of this, we're going to take, instead of a line, we're going to take our rectangle, and when we pull it up, we're not just going to pull it up. We're going to pinch it to a point, and that's going to give us a pyramid. Alright, so that looks like X, Y, Z. So your volume is something times X, Y, Z. Okay. So again, we just have all of our directions multiplied together, and the only question is, what is our shape constant? That's really all we care about. Well, it turns out this one is ridiculously easy, and we can kind of see it from what's happening here. We do have analogs in all of the other dimensions to this shape, because, so what we're doing is we're taking the shape that we got, the basic primordial shape that we got from the previous number of dimensions, we're taking it and pulling it to a point. So here we took a rectangle, pulled it to a point. Here we took a line and pulled it to a point. Here we take a point and pull it to a point. That also gives us a line. So the line is the one-dimensional analog to a triangle, just as much as it's the one-dimensional analog to the rectangle. They're equally related to this. And here, for existence, you take nothing and pull it to a point. So there's even the point itself. The point itself right here is actually an analog to the triangle when you think about it a certain way. Okay, so think about this. What the hell is happening? Okay, well, our numerator on our shape constant is 1. Our denominator is the number of dimensions we're in. Right? So over here, if I did 1 divided by 1, that would give me 1. That would be totally fine. That's correct. That works. If I do 1 divided by 2, that would give me this 1/2. That's totally fine. That's correct. That works. Over here, I have 3 directions, so I'm going to do a numerator of 1 and a denominator of 3. And guess what? That works. That's exactly correct. This 3, and this 3, and this 3 over here, and the fact you have 3 variables, it's all exactly the same 3. Just like up here, this 2, these 2 variables, and this 2 over here on this exponent, that's all exactly the same 2. It's not a coincidence that the 2-dimensional shapes are filled with 2's, and the 3-dimensional shapes are filled with 3's. The 3-dimensional shapes are filled with 3's because that's what the 3 dimensions is. The 2 dimensions are filled with 2's because that's what's happening there. 1 dimension is filled with 1's. There's really only one choice. It's so filled with 1's that there's only one thing happening. Okay, now, how about a cone? So that one, it's sort of like the pyramid and the cylinder at the same time. And I guarantee you, if you look this equation up in a book, it's going to be perplexing to you. You're going to look at it and say, why are those the numbers? But now, when we look at this way, it's actually going to make sense. Okay, so we have a circle base, so we're going to get pi on 4. Pi on 4, x, y, z. And it's like a pyramid, so we're going to get 1/3. So 1/3 of pi on 4, x, y, z. Hey. Because it is like the pyramid, and it is like the cylinder. So we get both the cylinder constant and the pyramid constant. Or you could think of it as we took a circle, which is going to be pi on 4 xy, the middle thing. We pulled it into a 3rd dimension, so that's the z. And as we did so, we scrunched it to a point. So that's the 1/3. All of the components of this now make sense. Everything in here has semantic content. This means something. This you can remember, even if you forget it. That 3 is the fact that you have 3 directions. That's what that 3 is. The pi on 4 is the fact that you have a circle. That's what the pi on 4 is. This one I can't explain as well. I'm sure there is an explanation. I just don't understand it. I don't have it. I don't know if anybody does. Probably somebody does. I don't by any means think that I am like the smartest person in the world and I'm the only person who knows any of this stuff. I've just never seen it explained by anybody else. So that's why I feel like it's worth sharing, because if I can't find it as a math teacher, probably not many other people could find it either, even if it does exist. Okay, so for a sphere, the volume of this guy, there's circles involved, so you're going to get pi on 4. There's 3 directions, so you get x, y, z. For a perfect sphere, all 3 of those directions are the same as each other, so it's just whatever cubed. Now, I don't understand why this is what it is exactly, but it is, so it's just 2 of these, so it's 2/3. So you can think of, if I took 2 cones and smushed them together, that would give me a sphere that would fit inside the same box. The same exact box that our original cone would fit in. If I took 2 of those, smushed them together into a ball, that ball would exactly fit inside that same box that the cone did. That's cool. I don't know. I think that's cool. I don't know why it's 2/3, but it is. And we can kind of play with this a little bit to get some nice approximations. So if we kind of treat the pi to be 3, then we can sort of pretend that these cancel out, right? So this is very well approximated by 1/4 of our 3 things multiplied together. And this guy, so we do that same trick, so we just have 2 on 4, well, that's a half. So this is well approximated by 1/2 of all 3 things. So the sphere is actually very close in volume to your triangular prism. It's a little bit more because the pi is on top and it is bigger than the 3. So it wins a little bit. It's slightly bigger than this in volume, but it's very, very close. And if you're trying to do these things with mental math, you just kind of want a ballpark estimate relatively quickly, that's handy. Just especially if one of these is an even number. Well, you're probably dealing with a perfect sphere instead of like spheroids or whatever. So if your diameter or whatever is an even number, well, that's easy. Just cut it in half when you multiply. Just cut one of them in half, right? So say it's 4, right? So I would have 4 times 4 times 4 times 2 times pi divided by 3 times 4. That's a pain in the ass. Or I could just say it's going to be a little bit more than 2 times 4 times 4. Or a little bit more than 32. If it's a multiple choice question, there's probably only going to be one that's just a little bit more than 32. That can actually end up getting you points on a test. That can actually end up, making your world a lot easier, just kind of recognizing these sorts of things. Okay, so come full circle. This is how exponents work. It is 1 times the base, exponent times. So 1 times 3, 4 times. 1 times 3, 0 times. 1 times 3, negative 4 times, or 1 divided by 3, 4 times. Boom. That's how exponents actually work. And it has analog in geometry because your shape constants, of which pi is sort of a bastard version, they are actually a form of that 1 that's showing up in your exponents there. So those ones there in your exponents. That 1 in your fraction that you've probably seen. That 1 in the 0 exponents that you've definitely seen and probably been like, why the fuck is that the thing? I don't know. Now there's a reason. Once we build up a philosophy of why this works, it turns out that it works even better than we could have hoped. So there you go. Oh, maybe that helps somebody. Who knows?